Hello, everyone. I'd like to go through section 1-4 with you on inductive reasoning, and not sure how sensitive the microphone is here. Kirby's in the background munching on some very noisy chew toys, so if you occasionally hear strange things in the background, that's him. Yeah, I never did like this. Suppose we start with a circle. Put a point on the circle. There's only one region. We put 2 points on the circle. We play connect the dots in every possible way. That splits the circle into two regions. If we put 3 points on the circle, and again, play connect the dots in every way possible, that splits the circle into one, two, three, four different regions. Now, mind you, the points aren't evenly spaced. Those regions don't have the same area. All we're really concerned with here is how many different parts is the circle cut into. So if we put 4 points on here, and again, connect the points, connect the dots in as many different ways as we possibly can, that splits it into around the outside edge here. One, two, three, four. And on the inside, five, six, seven, total of 8 different regions. So the question then becomes, when points are connected, the segments divide the circle into a number of regions. How does the number of regions change when another point is added? Okay. Inductive reasoning, okay, is very, very different from what you've been using for the most part in algebra. That would be deductive reasoning. For inductive reasoning, we're given information such as this. We take a closer look at the values and we try and figure out what the pattern is. Okay. So for part B there, it's saying using the pattern that you observed, make a prediction about the number of regions formed by connecting 5 points on the circle. Well, that's going to be interesting here now, isn't it? So if we start with a circle, maybe I need to move it over here. And we put on the circle, we already have 1, so now I need 2, 3, 4, 5 points on the circle, play connect the dots. But it's not just these across like this. We have to go and there. That, I think, should be all of them. So now it's a matter of how good are your counting skills. So what is your prediction here? If you said 16, you're right on track. Okay. So again, we're trying to describe this, I don't know, maybe algebraically. So for 2 points, there were 2 regions. For 3 points, there were 4. For 4 points, there were 8. For 5 points, there are 16. It seems like for every new point, we take the previous number of regions and multiply by 2. Again, the pattern here goes 1, 2, 4, 8. Using inductive reasoning, our next one there should be 16. So inductive reasoning, the way they define it here, is a way of thinking that reaches conclusions based on a pattern of specific examples or past events. Okay. So again, it's not too tough to do with numbers here if we can figure out the pattern depending upon what type of a sequence of values we have here. So 88, 82, 76, 70, 64. Clearly they're decreasing. From 88 to 82, it went down by 6. 82 to 67, it goes down by 6. 76 to 70, clearly it goes down by 6. So yeah, we have a consistent pattern that goes all the way through, and we can use that pattern to predict the next two terms simply by taking 64 and subtracting 6 to get a 58. 58, subtract 6 and get 52. 3, 5, 9, 15, 23. What's the pattern here? Well, from 3 to 5, that's an increase of 2. 5 to 9, that's an increase of 4. 9 to 15, that's an increase of 6. Okay, now we've got a pattern established here by the successive differences. We're going up by even intervals here. We're adding 2, add 4, add 6, add 8. So for the next one, we should add 10 and get from 23 to 33. Then from 33, add 12 and get to 45. So a conjecture is, I don't know, in some cases, it's described as an educated guess. Sometimes in science class, you will hear a conjecture is fairly synonymous to a hypothesis. So a conjecture is an unproven statement or rule based on inductive reasoning, and the key thing here is, sure, we can come up with conjectures all we want. You have to put them to the test. Okay? So if we take 2 dots, if we take 6 dots and arrange them in a rectangular pattern here, the first term will give us 2 dots, the second term will give us 6 dots, the third term will give us 12, the fourth term will give us 20. Describe what's going on. That's what a conjecture is. So the number of columns up and down is one more than the term number. Okay, so for our first term, we've got 2 columns in 1 row. For the second term, we have 3 columns in 2 rows. For the third term, we have 4 columns, 3 rows. The number of rows is the same as the term number. How do we figure out how many dots there are? We simply have to multiply. So if it's n number of rows, there will be n plus 1 number of columns, and then it's simply the product, n times n plus 1, or for those of you that still remember how to distribute, n squared plus n number of dots. Okay, now if we put that to the test here with the fourth, if we put 4 in place of n, 4 squared will give us 16, 16 plus 4, 20 dots. So our formula is descriptive. Okay, so now here are some recent election voter turnout numbers from a particular precinct. So we have a nice table telling us here for the past 7 elections or so, total number of residents in this particular precinct, and oh my goodness, the pitiful, despicable voter turnout numbers here. Oh, that's somewhat depressing. All right, so we look for a pattern. Okay, now just comparing the raw numbers, the total number of residents went up by this many people from one year to the next to the next, and then the voter turnout went up by, I'm not sure that's a fair comparison. Okay, with unequal numbers, we should probably look for ratios. So if we take the number of votes cast divided by the number of residents, let's see what those numbers turn out to be. Okay, so for the first one in our chart here, that's 0.110. For the next one, 0.109. For the third year in our chart there, 0.110, 0.111, 0.112, 0.109. So it looks like only about 11% of voters who are eligible here are actually good citizens and doing their civic duty. So use our conjecture here, predict what's coming next. In year 7 of this, we have 7,786 residents. If voter turnout there is approximately 11%, now careful, we can't say that there are going to be 856.46 voters. Okay, we could either round that off and say our prediction here is 856 people, or you could say our prediction here is more than 856 and then round up to the next integer. I would accept either of those, again, depending upon how you explained it. You just say rounding that number off to the nearest integer, or it's going to be more than this, so we're going to round up to the next integer. Either of those can be justified. So again, inductive reasoning, we're looking for a pattern, we're coming up with a conjecture, and then we're putting that conjecture to the test. Okay? Now, this has been done time and time again with so many different things in mathematics. When we find a conjecture that is true 100% of the time, that becomes a theorem. Okay? It's really hard to prove that a theorem is true. To show that a conjecture is false, that's really easy. We just need one counterexample. But we've got to be very careful. We have to be very specific about how we come up with that counterexample. A counterexample is a way that shows that a statement or a conjecture is false. We need just one exception to our conjecture. Okay? So, suppose a polygon with diagonals always has two fewer diagonals compared to the number of sides. Okay, so if we take a look at a quadrilateral that has four sides, now again, a diagonal connects point to point here so that they're connecting non-consecutive points. So from this point to this point, those are consecutive. That's one side of our nice quadrilateral. That doesn't count. So if we go from this point across, that's a diagonal. What happens if we look at five sides? No, hold on. So we've got five sides, and then we put in all of the diagonals. It turns out to be equal. So the conjecture, a polygon with diagonals has two fewer diagonals as the number of sides. There, that's it. We can stop. Okay, we have found one situation here that shows that the conjecture is false. It doesn't have two fewer diagonals compared to the number of sides. The number of diagonals is equal to the number of sides. The conjecture is false, and here is the counterexample. Okay, as I said, coming up with a conjecture is one thing. We've got to put it to the test. Okay, so let's take a look at a couple of these here. A polygon with 4 congruent sides is a square. That's our conjecture. Now, if you think it's true, then you have to demonstrate that it's always true. If you think that that conjecture is false, we need to explain a counterexample. Okay? Have you guys heard of a rhombus before? A square has 4 congruent sides and 4 right angles. Okay, so it's possible for a polygon with 4 congruent sides to be a square, but it doesn't have to be. Okay, now another thing here I want you to pay close attention to here. For a good counterexample, you have to follow the conditions in the first part. The first part of it has to be 100% true, but it's that second part that has to be false for a good counterexample. Okay? So we need to come up with some kind of a polygon that has 4 congruent sides, but it is not a square. So again, a rhombus is a good counterexample. Okay? If a number is a multiple of 9, then the sum of its digits is a multiple of 9. Okay, so again, if you think about, say, 9 times 2 is 18. 1 plus 8, that's 9. Okay, that works. 9 squared is 81. 8 plus 1, that's 9. That seems to work. 9 times 12 is 108. Yeah, add those digits together and that gives us 9. 9 times, say, 313. That seems a random thing to choose. 2,817. So if we add 2 plus 8 plus 1 plus 7, that gives us, oh, wait, 18. That's also a multiple of 9. Okay? 9 times, amazingly, 1,105 will give us 9,945. Add together the individual digits. 9 plus 9 plus 4 plus 5 gives us 27. That's a multiple of 9. Okay? So it would appear here that conjecture B is in fact true. We will get into how to prove something. That's a very formal process, and at times that can be kind of tricky. But all we're looking for here in inductive reasoning is looking for a pattern, trying to come up with a conjecture that describes the pattern that you see, and then you put that conjecture to the test. Okay? If we can find a counterexample, one counterexample is all we need to show that something is false. To prove that something is true, we need an entire formal proof, and we'll talk about that some other day. So if you could then go to the assignment there and realize, take a look, do your best to answer these questions from section 4, and we'll see how you do. Good luck.